Waiting for slides. While I'm waiting for the slides, I'll thank, there we go. Thank Dr. Scott, Tori Johnson, Lori McDaniel, Dr. Nick Zeppos, and the sponsors of this inaugural SEC Symposium for the opportunity to talk about the role of plasmonic nanocomposite metamaterials for sustainable energy technologies. Let me start by providing two short definitions. What is a plasmon? A plasmon is coherent oscillation of delocalized free electrons at the interface of certain metals and an adjacent or neighboring dielectric, which is driven by incident, resonant electromagnetism and opposed by a Coulombic restoring force. Now, what's a metamaterial? Metamaterial is an artificial, engineered material composed of meta-atoms, in this case, gold nanoparticles, which exhibit unusual properties that are not found in nature. Our plasmonic nanocomposite metamaterials couple plasmons to diffraction or diffracted modes in two-dimensional gratings. This creates strong local electromagnetic fields, and we use those in a number of applications for sustainable energy. So I'll start out today by outlining a national blueprint to engineer sustainable energy based on metamaterials. I'll summarize the grand challenges in sustainability engineering briefly, that was done earlier today, and ask whether recent advances in plasmon engineering can meet these needs. I'll identify what's currently missing in plasmon engineering of band structures and metamaterials. And then I'll review initial results and ongoing thrusts in our research area in our lab and point to future directions. So my colleague, Ram Gupta, who is from Auburn University and currently serving as a program director at NSF, is fond of saying there is one source of sustainable energy. And what we typically think of as renewable energy sources are reservoirs and carriers for incident solar radiation. Each year in the US, we currently use close to 100 quads of energy. One quad is equivalent to 8 billion US gallons of gasoline or 36 million tons of coal. Nearly 56% of energy consumed is rejected, primarily as waste heat, during generation, transmission, and use. About 1/4 is used for transportation, and just a little less than 1/4 is used in industry. Petroleum constitutes more than 1/3 of energy used, and we heard about some of the difficulties of petroleum earlier today. Natural gas and coal-fired electric plants combine for nearly half of energy sourced, and less than 10% total comes from renewable biomass, hydro, geothermal, wind, and solar, plus nuclear. The current administration's fuel efficiency standards and support for cogeneration are intended to redirect this waste heat to useful purposes. Compressed natural gas, ethanol, and electric cars are encouraging replacing petroleum with greener energy sources. Carbon sequestration at centralized power facilities is under development to reduce source emissions. And wind energy and solar photovoltaic and photothermal sources have increased dramatically in the past few years under the current administration. Dr. Sam Baldwin outlined earlier in substantially more detail the positive impact of developing these technologies in the US. At the same time, developing new technologies that support sustainable energy can promote economic development, as Ambassador Shine discussed. There's further progress to be made in sustainable energy technologies. Particularly large gains could be available in reducing waste energy during production and during use, as mandated by the 55 mile per gallon CAFE standards. Gains are also possible in increasing efficiency of conversion of renewables, such as cellulosics, to energy reservoirs and carriers, particularly as transportation fuels, as mandated by RFS2. And I'll talk about applications of plasmonics in that area in just a bit. What makes energy sustainable is that it meets our present needs without compromising the ability of future generations to meet their needs. Professor Bill Adams at Cambridge uses this Venn diagram to illustrate that sustainability occurs when current social, societal, and economic needs are balanced together with similar future needs. We can use this Venn diagram to strategize progress in sustainable energy using metamaterials. First, economic needs can be measured in terms of dollars per watt or dollars per megawatt levelized to account for externalities, as one of our questioners talked about earlier. That includes carbon sequestration, construction of facilities, and installation. The preceding energy use diagram showed that society primarily uses energy for transportation. So energy-dense fuels can be measured in terms of megajoules per liter or kilogram. The environmental impact can be measured in terms of percent conversion efficiency from the sun to that source or reservoir, as well as by carbon redox level. Taken together, these measures indicate that natural gas, as shown here, with a redox potential of -4 and levelized cost of $93 per megawatt hour, is closer to sustainability currently than oil or coal. However, its energy density is only 22 megajoules per liter, about half of that of oil, which decreases its social benefit for transportation. Biofuels have higher energy density, but are more oxidized than natural gas, and so have a lower levelized cost per megawatt. Hydrogen gas is a poorer energy carrier, and it's currently further from ideal. Solar, wind, and hydropower strongly favor the environment, but lack transportability due to low battery lifetimes. Levelized costs of solar technologies currently is particularly high. So by quantitating the Venn diagram in this way, we can identify the grand challenges in sustainable energy, as outlined by the National Academy of Engineering. The first is to make solar energy economical. This will be the focus point for our improvements in plasmon engineering. The second is to sequester carbon dioxide from point gas and coal sources. And third, to improve batteries to make green energies transportable. It's important to recognize that there is currently no available energy source that is both efficient, portable, and economical. So work is ongoing to develop cost-effective models to design more sustainable alternatives or permeations of the existing reservoirs and sources. Promising strategies for transformative improvements in sustainability using metamaterials can be found in Pasteur's quadrant. In this quadrant, a quest for fundamental understanding, or basic research, is directed toward unmet needs of several reservoirs and carriers of sustainable energy. So first, let's ask, why plasmon engineering? What's so useful about that instead of other basic technologies? And then we'll consider what's currently missing in the field of plasmon engineering. So why plasmon engineering? Plasmons produce one of nature's most intense local electromagnetic fields. It occurs within 100 nanometers of the interface between the plasmon active metal and the dielectric. Now, 100 nanometers is about the distance of 1,000 water molecules end to end. These intense fields are being evaluated for next-generation optoelectronic circuits and are successfully being applied to thermally ablate tumors in vivo. But these fields are limited in current solar photovoltaic and solar thermal applications because they only occur at narrow plasmon resonance frequencies, and they only occur at the metal surface itself under those conditions. They are also highly dependent in more complicated structures on incident wavelength, its direction, for example, polarization. In terms of photocurrent losses, the metal particles block incoming light, cause a shadowing effect. They recombine with previously generated electron holes and pairs and induce ohmic and thermal losses. As a consequence, there are no current plasmonic designs which are solar efficient, energy dense, and economic. Furthermore, there are very few inexpensive models available to advance design or fabrication of these next generation plasmon systems that could take advantage of these extraordinary electromagnetic fields. The iterative process of modeling Maxwell's equations to design potential plasmonic structures, fabricate prototypes, and then evaluate their performance has several current deficiencies. First, Existing finite difference time domain and dipole approximations are computationally expensive. They do not bridge multiple length and time scales, and they misattribute effects of lattice elements on the outcomes of the simulation. Second, current top-down fabrication methods use multi-million-dollar equipment at extreme environments in batch processes that are not well suited to economic large-scale manufacture. These methods produce variable results and are employed with just a limited understanding of the underlying material chemistry and physics. Third, current evaluation methods produce massive and unarticulated data sets that include a large number of inexplicable effects and few metrics to evaluate progress in this area. So the complex outcomes that result from this process disconnect these models, designs, and prototypes from actual devices and prevent developments in the real world. What's needed in the field are fast, accurate, multi-scale simulations that directly attribute meta-atom size, shape, composition, and spacing to band structures like the Fano resonance. We need inexpensive fabrication methods that are scalable to roll manufacturing and that give reproducible results based on an understanding of underlying fundamental materials chemistry and physics. Third, we need articulated evaluation methods that directly, rather than indirectly, probe key attributes to validate our models. And finally, we need interactive visualization tools that bring this complex information together, bridge the models and the prototypes to devices with searchable databases. There are very few labs in the world today that integrate modeling, design, fabrication, and evaluation end to end. Such integration would speed the development cycle through rapid feedback and feed-forward of information. So in my nanophotonics lab, we are pursuing a multidimensional systems approach to plasmon-engineer band structures in nanocomposite metamaterials for sustainable energy. We consider particular sustainable energies that could benefit from plasmons as system test beds, and we integrate them from the quantum photonic scale all the way to macroscopic scale devices. So for example, solar photovoltaic and concentrated solar thermal systems are considered as one test bed. Nano bio refining systems, all the way from algal diatoms to large-scale biofuel recovery, are considered as a second test bed. Third, learner-driven education to transform eager students to engineering professionals in sustainable energy is a third test bed. And finally, related technologies are a fourth test bed. Now, the development of these systems is driven by advances in enabling technologies that underlie these test beds. The enabling technologies for these systems are multi-scale computation, metamaterials, bottom-up fabrication, and multi-scale evaluation. Advances in these enabling technologies are driven by new fundamental insights in knowledge. For the above technologies, these fundamental knowledge areas are an enhanced understanding of electrodynamics, particularly at interfaces. How do the electrons get in and get out of these materials at the edges where the models typically break down? Plasmonics, particularly as it's related to diffraction coupling in metamaterials. The materials themselves and how their structures contribute to both the optical and the electrical properties. And finally, resonance microscopies and spectroscopies with nanoscale resolution. Then we identify key barriers at each level of development, and we form partnerships with stakeholders in academia, government, and industry to accelerate advances in this area. So at this point, you're probably wondering whether such a complex systems-level approach is justified. So let's consider 4 case studies. First, we've made significant advances in computing band structures in Fano resonances. Recall that Fano resonances are these interactions between the oscillating electrons on the plasma and the diffraction inside the grating of our two-dimensional system. Our specific purpose has been to identify the effects of meta-atom composition and geometry, as well as the system geometry, like the grating constant, on these band structures. In the past, there have been few predictive analytics for phaneresonances in nanocomposite metamaterials. Most researchers solve Maxwell's equations, specialize for these systems fully with finite difference time domain. They get their results and employ a number of approximations that introduce a number of errors that are often explicable and have a difficult time correlating the simulation with the outcome. In addition, there's an incomplete understanding of key material attributes. So in 2007, I began working with Ben Taylor and my group and continued in 2009 with Braden Harbin, who's shown here, to reduce Maxwell's equations for plasmon metamaterials in both random and square assemblies into a rapid semi-analytic format. This multi-scale formulation used constitutive relations to coarse grain, finer scale optical and electrical properties, in particular polarizability. Drew Jarnett joined our group in 2010, and he extended these relations, which were originally conceived for dipoles, to multipole behavior, including quadrupoles and beyond. And in 2011, Drew also identified discrete diffracted phase modes for these diffracted waves that are populating successively higher energies in our metamaterials. And they're shown as the oscillating lines in these spectra. Now, as an interesting tidbit, work in this area is not new. There were simulations that were done in approximately 2004 using full finite difference time domain. When those researchers did those simulations, they saw this oscillatory behavior, and because they had shortened or restricted the full finite difference time domain, they assumed that these oscillations were a result of error in the simulation. So they used boxcar smoothing as they reported their results to get rid of these noisy oscillations. Turns out the oscillations were coming from the diffraction themselves, and because there was no direct attribution, they erased the very thing that would help them know what they were looking for. So this, taken together, these advances constitute a rapid, semi-analytical coupled dipole approximation. This rapid computational analysis method directly attributes the effects of meta-atom composition and geometry, the size, shape, and nanoparticles, the incident energy, and the lattice constant on phano-energy and band structures. This includes unique band gap saddles that bridge multiple diffractive phase modes. And I think I have a laser pointer up here. It's worth stopping and just pointing this out. There we go. This sort of plasmon resonance has been extensively reported in the literature. It's a single peak and it occurs in the infrared, which makes it interesting for a number of applications. But these saddle-type structures have never been reported or evaluated. We had seen them in our laboratory. I assume that other researchers had as well. But without an adequate description, you don't go around reporting two peaks where you think theory says you should have one. And now we can in fact show what the origin of these is actually the overlap of the polarizability on the adjacent lobes of the diffracted photons. Makes perfect sense when I say it, but that's a result of this direct analytic computation that we're able to show that. So those saddles are shown there in two-dimensional and also in three-dimensional geometries. This analytic method allows rapid optimization. Now everybody uses that word rapid, so what do I mean? This particular graph shows 11,000 different simulations. These are distinct simulations using different nanoparticle lattice constants and different particle radii. These are infinite lattices. So these are large simulations, virtually impossible to do with finite difference time domain. And here are 11,000 of these. They were run to rapidly optimize the design of metamaterial lattice constant and particle size in order to maximize this phano-resonance effect. This analytic method can predict phano-resonances a priori, and the predictions match both the magnitudes and the trends in intensity and breadth of the measured modes. This work was done in Ken Crozier's lab at Harvard a few years ago. So overall, this fast, new, inexpensive computational approach predicts metamaterial band structure, speeds prototype design, and it directly attributes physical features. In parallel, we began developing a new metamaterial fabrication strategy. What's the use of having a great model? Unless as an engineer you can build it. We started that in 2007. Metamaterial fabrication consists of complementary lithography and deposition steps. Currently, it relies on expensive electron beam and vacuum deposition. The operations occur in batch mode under extreme conditions not amenable to economic large-scale manufacturing, which would allow cost parity for SolarX testbed. So beginning in 2007 through 2010, Wan Mi An and our group developed inexpensive bottom-up lithography and complementary electroless plating methods that for the first time produced ordered arrays of self-assembled adherent meta-atoms with smooth, low-loss surfaces in a spherical geometry. This was published in ACS Nano in 2010. Low-cost, bottom-up lithography and deposition are game-changing technologies that open the door to cost parity for metamaterials through economic roll-to-roll manufacturing. These advances were based on improved understanding of underlying material chemistry and physics. So then we move forward to characterize and reduce optical losses in bottom-up deposited meta-atoms and integrate our new method with existing lithography approaches. Existing approaches deposit agglomerated metallic meta-atoms that dissipate plasmon energy via incompletely understood mechanisms. So Wan Mi An worked with Philip Blake and Gyung Zhang, shown here, over 4 years, to show that conventional E-beam and a new continuous plating method could be substantially enhanced. Their new protocols allowed continuous, predictable meta-atom deposition with improved surface uniformity, shape, and adherence. These have been demonstrated to reduce both optical and thermal losses. So with improved modeling and fabrication tools, we needed better evaluation of local band structures in metamaterials. Existing evaluation tools provide information at the millimeter scale and at time scales on the order of minutes. They cannot distinguish fast effects of particular fine-grained architectures at the hundreds of nanometer scale. So from 2008 to 2012, Philip Blake developed nanoscale optical spectroscopy systems to isolate band structures from individual meta-atoms and small groups within larger lattices of nanocomposite metamaterials. The longest running end-to-end integration of modeling, design, fabrication, and evaluation of metamaterials in our lab was initiated in 2006. It's been to quantify the efficiency of energy transfer from photons to plasmons and from plasmons to phonons. These efficiencies were previously undistinguished in metamaterials, particularly in open systems. There was and remains incomplete understanding of the impacts of these efficiencies on optoelectronic performance. With Wan Mi and Gyung, we successfully modeled, designed, and fabricated and evaluated these efficiencies in both liquid and solid nanocomposites. Aaron Russell, a Native American graduate student, extended this work to open systems in 2008. This plot shows a non-dimensionalization of metamaterial temperature increasing over time as it's heated by localized plasmids. There's excellent agreement between the a priori model and measured data. The model explains virtually all the variation in the data for diverse gases and liquids that are important in the bioeconomy. This end-to-end integration resulted in predictable plasmon heating efficiencies of virtually 100% in improved metamaterial prototypes. Overall, our multidimensional, complex systems approach to developing metamaterials by fast iteration of the cycle of modeling, design, and evaluation has been applied to quite a large number of systems and geometries in our lab, and I show a few here. So what does the future bring? At present, we're investigating plasmon meta-atoms in van der Waals and soft materials. We envision applications in optoelectronics and synthetic biology that could provide significant advances in sustainable energy. We're also working to improve resolution in plasmon sources and imaging systems, which has several possible applications in nanobio areas. We're particularly interested in using metamaterials to reduce energy consumption in large-scale biofuel, petrochemical, and wastewater recovery processes. we focus on distillation and memory-based recovery operations for bioethanol and biobutanol, where energy use is high, up to 3 quads in the US annually for distillation alone. That's 3% of the energy that we use per year. Our working hypothesis has been that direct, pinpoint, nanoscale heating of interacting molecules in these large-scale systems by plasmon metamaterials could effectively decouple thermal transport from mass transport and make possible reductions in thermal losses from bulk heating of up to 10-fold. Mr. Stephen Mearshak talked earlier about the potential impact of the Southeast in cellulose biofuels. This represents an application of particular interest to our region. We've also identified a number of key challenges to be overcome for significant progress in this area. We recently partnered with Professor Padma Vasuvadan at the Institute of Technology in Delhi, who has a vigorous program in sustainable energy and agricultural and energy technologies. And any of you who are interested in this should love to have additional partners here in the Southeast. So, how is the multidimensional systems approach for plasmon engineering of band structures working currently? Jeremy Dunklin in our group was recently awarded a NASA grant to purify and recycle wastewater with metamaterials. Pioneering work involving 9 students in my group was instrumental in bringing the NSF EPSCoR Award in Green Energy to the University of Arkansas. Barry James, shown in your right on this photo, a recent graduate student in my group, won an international IBK Business Plan Award for a startup to support educational advances for young people. And Keith Berry, a Native American undergrad in my group, was recognized by NSF for his publication on meta-atoms and biomedical polymers and nanotechnology last year. And I have to shout out to Marty Matlock, who's here. Thank you for introducing us to all these wonderful Native Americans. In this summary, we have a multidimensional, systems-level approach to plasmon engineering of band structures in nanocomposite metamaterials. It's allowed significant progress. Needed advances have been made in multi-scale modeling, bottom-up lithography, fabrication, and integrated evaluation to support sustainable area in 3 test beds: solar photovoltaics and solar thermal, micro to macro biofuel refining, and engineering education. Plasmon-engineered band structures show promise as solar-efficient, energy-dense, economic, foundational technology to support game-changing advances in sustainable energy. Currently, there's an open solicitation at NSF, I'm putting on my other hat, for proposals to support development of a wide range of technologies that advance sustainable energy. So check online for more details there. And please note there's currently an opening for an NSF program director in the area of sustainable energy. Please see me afterward or contact me for more information about this position. I certainly acknowledge generous support from numerous sources at the university, state, federal, and private levels, wonderful contributions from collaborators in many departments, and most of all, current and prior group members. Thank you for your attention. Be happy to address any questions.
Thanks, Keith. Great example of integration from basic to applied, research, education, everything.
Thanks.
Beautiful. It's open for discussion. Here it comes.
Thank you for the talk. Robin Rogers, University of Alabama. I was curious about the Venn diagram at the beginning, and your comment about the environmental piece of that seemed to only look at quantizing the efficiency. If I understood what you said, how efficient was the conversion of solar? Mm-hmm. My understanding of sustainability and green chemistry and the like, there's a lot more in that environmental sector that goes Absolutely. To the degradation of the environment more than just the efficiency of conversion. How would you integrate that?
That was meant as a brief overview to point us toward those grand challenges that were identified by the National Academy. I certainly agree with you. I think the talk this morning that was given by Dr. Baldwin went into much more detail, and Steve's talk as well, and I certainly would refer you to them for more detail. It was meant for illustrative purposes only. I think I was not expecting the kind of wonderful introduction that we had in terms of background information earlier. So you could certainly quantitate those and get a better multi-dimensional picture of the types of challenges that are represented, and that would be useful for, you know, preparing a strategy for moving forward. And I'm happy to talk more about that afterward to learn from you.
Other questions? Okay, oh, one over here from Josh. Then we'll move on.
Keith, thanks for the great talk. Josh Gladden, University of Mississippi, in case you forgot. Your cycle of improving the efficiency of sort of the materials development cycle from modeling, simulation, to fabrication, to characterization, and so on, seems to tie in with the Materials Genome Initiative. I'm not sure if you're familiar with this presidential initiative.
Mm-hmm.
And if you are familiar with it, I was just wondering if you might speak for a moment about that and if you see a relationship between the two.
There is certainly quite a bit of support at NSF and other federal agencies for the Materials Genome Initiative. I'm not the program director over that area, and so I can't speak to that directly, but developing materials that meet particular needs, sustainable energy, one of those, has a high priority right now with federal agencies. And I go back to your talk on the development of thermoelectrics, piezoelectrics, and some of these very unique materials as examples of ways that they can benefit not only sustainable energy, but very many other areas in our lives. So I think the future is bright for materials energy and for funding initiatives in this area for years to come, for those of you who are graduate students or maybe professors looking for areas to diversify in. But thanks for the nod to the Materials Genome Initiative.
Okay, let's thank Keith for a very nice talk.